Good afternoon, everyone. Today I'm going to talk about what it takes to make in-memory computing enterprise grade. And in order to talk about this, we need to kind of put down some ground rules. So everyone thinks enterprise grade is something different. I'm going to use a definition. You may not agree with it, but I'm going to use a definition. So there's four major pieces to what I'm going to be talking about. That's scalability, reliability, security, and integration. And those are the pieces together that make something enterprise grade. So let's define what I think these things mean. And some of these definitions I've pulled from things like Investopedia and some of the other Wikipedia type sites. Scalability is basically the ability to increase what something does. So how much it processes, how much it can ingest. And in memory computing, scalability isn't just about adding boxes. It's not just about spinning up more VMs in Amazon. It's about being able to deal with increases in volume from the amount of data that's coming in, increased amount of processing, potentially on the same data, but you're processing it more, an increase in the amount of in-memory data that you may have, and an increase in the amount of stored data that you may have. And all of those together need to be considered when you're talking about scalability. Now, reliability is the ability of a system to be able to do what it's supposed to do without dying. And for you to be able to rely on that, for it to be there when you need it to be there, and if there are failures, for it to be able to cope with those failures. And so when we think about that in memory computing, there's reliability of ingestion. Do you process everything you get? Do you miss anything? Are you going to lose things? Reliability in processing. Can you spin up another processor if you lose one? So can you continue processing in the case of failure? Reliability of results is ensuring that you do generate results when you're supposed to, and ideally that you can do exactly once processing. That for any given input amount of data that will generate results, that it will always produce the same results, and you'll only produce those results once. Security, obviously, is really important for any enterprise-grade system. It's one of the things it's usually measured by. And for in-memory computing, it really comes down to, can you use authentication and authorization to restrict access to what people do and what people see, what people have access to? Can you protect your resources wherever they are? And can you encrypt data when it's moving? Encrypting things in memory isn't always necessary unless you think people are going to go around poking around in memory. But encrypting things as they're moving between nodes is essential. So encryption has to play into it. And then finally, integration. And integration is really, you have this in-memory computing platform. How does it work with everything else? You have this beautiful platform, but it's useless if it's completely isolated. And you can't get data into it from your existing systems. You can't take data out of it to your existing systems. You can't integrate existing processing you may have. And if you can't do all of that, then you just have this in-memory computing platform that just sits there not doing anything. So you need to be able to integrate with what you have in order to actually make it fit into the enterprise. So I'm talking about all of this from the context of a company that's built a full end-to-end in-memory computing platform. So while this is not a product pitch, I'm using what we have done and the lessons that we have learned and the best practices that we have used to actually talk about some of this enterprise-grade things. So our platform deals with a lot of those things that I was talking about because it is an end-to-end platform. It is in memory, and it does continuous ingest and processing and enrichment of high-speed streaming data. So when we're talking about all those aspects of enterprise grade and how they apply to the various pieces of an in-memory computing architecture, I will refer to some of the things that we have done and the best practices that we have found. And the in-memory platform doesn't just exist on its own, it does play a role between some of the other platforms that you may see. So you have kind of the legacy stuff, if you like, with ETL jobs and operational data store or data warehouse that's typically batch and high latency and slow moving. And then you have kind of in the middle your big data applications, which may be dealing with a lot of non-traditional data, but again are typically more batch oriented. And then you have the real-time applications that are being powered by a streaming in-memory platform. And that streaming integration side, that works with the big data and the existing legacy in kind of a two-way thing. You can store stuff there and you can load it back for using context that you may have in your in-memory processing. And so to talk about all of those aspects of enterprise grade, I'm going to break down an in-memory architecture into a number of different pieces. And so at the bottom, you'll see one of the most crucial things is a high-speed messaging layer. If you're going to move data around from one place to another, you need a messaging layer, and it needs to be fast if you have a lot of volume. So internally in our platform, we use ZeroMQ for non-persistent high-speed messaging and Kafka for persistent high-speed messaging. Then if you want to join in-memory data with external data, you're going to need an in-memory data grid. And there are a number of companies here that have in-memory data grids, right? We actually use two different implementations of in-memory data grid that have different characteristics for different reasons. One we use for metadata and control, and for clustering. Actually, we use the clustering capabilities of Hazelcast for building our cluster. And so we utilize Hazelcast for controlling what's happening in all of our applications that are running in our platform. And then we have a high-speed, scalable, very controllable in-memory data grid for loading in external data that you want to mix with your streaming data. And these two in-memory data grids have different characteristics, and that's why we chose to do one way and one the other way. And we'll talk about some of the enterprise-grade aspects of these things as we get into the rest of the presentation. In that middle section there where you see multiple instances, all the servers have integration with all these pieces, right? The lines that go across, they're all distributed. But then on each of the servers, you can do things like ingestion and processing and enrichment and analytics. And those are things that you're actually doing in memory on those particular machines that make use of the rest of this architecture and the rest of this infrastructure. And then when you have generated stuff that's interesting, you probably want to store it somewhere. And we utilize Elasticsearch for our result storage for basically, because it's scalable, and because it will pre-index everything that we throw at it, and we can get results back really quickly. We can search for things, and we can run queries against it. So that kind of storage tier, whether it was Elasticsearch or some other persistent storage technology, has different characteristics as well that you have to consider. So with this kind of architecture in mind, we're going to talk about each one of those layers and how they have to meet all of those enterprise-grade characteristics. So let's think about scalability first. So on the data ingest side, you need to be able to scale up to receiving large amounts of data. And what we found was we have like a server technology, and our server is capable of doing everything you saw in that stack. So that's a lot of software. And because it's capable of doing everything in that stack, it's also able to hold large amounts of in-memory data. It's able to do a lot of processing. It's able to store a lot of stuff on disk. Now, if you ask people in enterprises, can I put this big server that can do all these things on your web server? then they'll probably say no, because they don't want something that uses lots of memory, lots of CPU, and lots of storage running on their production web server machines. So we have these lightweight collection agents that are designed specifically to be very low impact, and their job is just collecting stuff and sending it into the rest of the cluster. So that's kind of a way of dealing with scalability of ingest, is kind of minimize the impact that you put onto these endpoints and just do some simple collection and maybe some filtering on the endpoints before moving it into the rest of the cluster. Now, if we were talking about IoT, then things start to get a little bit different, because with IoT data, not only do you need to kind of collect from a lot of these endpoints, you may want to do some additional pre-processing, because a lot of IoT data can have a lot of redundancy in it that you may want to strip out before you move it into the rest of the cluster. So in those cases, maybe if you're running stuff on an IoT gateway, you may want to do some more of the initial processing before you move it somewhere else. The high-speed messaging layer, how do you go about making that scalable? So there's a few pieces that we really focused on in order to get this to work. The first is serialization. Now, data, when it's moving from one place to another in the network, it goes across as bytes. Well, it doesn't even go across as bytes. It goes across as fluctuations in an electrical signal, but that's kind of really low level. So it has to be turned into something that can go across the wire. And in the Java space, serialization is something that can be slow, as is a fully Java architecture. So when you're moving stuff from one place to another, you really have to care about serialization. And there's a number of different serialization libraries out there. It's worth benchmarking each one and kind of looking at your characteristics and looking at the best way of getting data from one place to another. We standardized on Cryo as our serialization layer, because it was the fastest thing that we found. And we wrote optimized code for Cryo to serialize things really, really quickly. But there are other approaches that may work as well. But serialization is definitely something you have to care about. Partitioning is also important, because when you're moving stuff from one place to another, and you've set up a number of processing nodes that can process the data, you'll probably want to partition the data so that it does things consistently. So an example would be if you had a huge amount of stock trades coming in, you'd want to partition things by ticker symbol so that the same symbol would always land on the same node. And that way you can start doing your aggregates and other calculations on one node without having to worry about your symbol appearing somewhere else. Now that can cause issues occasionally. You may want to have different levels of partitioning. I think there was an issue when Facebook went public and the servers couldn't handle it because all the Facebook trades were happening on one node. So you may have to have more advanced partitioning schemes in some circumstances. Non-blocking I/O is another essential part of high-speed messaging. And a way of backing off as well. So if your processors can't handle the throughput that's being sent and you have a backlog, then you need to somehow be able to back off what you're actually sending in. And that could just be queuing things up earlier on, maybe spilling things to disk before you actually send them out in order to actually handle the fact that your querying, your processing layer can't handle the throughput you're trying to throw at it. Now obviously, if that's the case, you may want to further scale the processing layer to handle the throughput. And reliability is also kind of an essential part of scalability. Because if your nodes go down, you need to be able to maintain the throughput that you have for your scale, and you need to be able to do that in a consistent way so you don't lose stuff. And with persistent messaging, because it is persistent, and if things do go down, then you might find yourself coming back up on another node or restarting. You face the danger of not doing exactly once. So you face the danger of sending the same thing again, not having known that you've already sent it. So you need to have ways of understanding what you've actually sent on persistent messaging and making sure that you don't send the same thing again. And that kind of falls into the reliability side as well. The metadata side of things is the things that handles our clustering, and it handles synchronization between nodes, and making sure actions happen in the right places within a cluster. And so it's this that kind of enables the hot clustering, so you can basically add a new node and it will register itself with the cluster. By default, we utilize the kind of multicast type of scenario, right, where you just start up a server and that server talks to all the other servers and tells, say, hi, I'm here, and then there's a single service that's managing within those servers that works out what services need to run on what servers, whether you need to do additional repartitioning of data or load distribution or other things when a new server starts up. We also use the metadata control in memory data grid for distributing Java bytecode. Now, our platform works, a fair proportion of it, by dynamic generation of Java bytecode, not loading stuff from jar files, but generating new code in memory in order to actually do certain processing. Now, if you're doing that, then you need to make sure that that code exists on all the machines in the cluster. And you don't want to generate it everywhere. So we actually have a distributed class loader built on top of the in-memory data grid that you basically define a class once and it's visible across the whole cluster. The in-memory data grid that we use for context, that was a slightly different beast. The key thing there was that in order to actually get high throughput, you don't want your context cache to be doing remote lookups. You want to try and make sure that when you route an event, that it lands on the right node that actually has the data locally in memory within that cache. So the way of doing that is by using a consistent hashing algorithm across the messaging layer and across the cache layer. Now, this is a little bit more complicated in our platform because we don't always treat the whole cluster as the place where you're going to be running stuff. When you deploy things within our platform, you can choose a subset of the nodes within the cluster to actually run things on. So that partitioning of events and the partitioning of data has to also take into account kind of this sub-clustering capability. And we also have to be able to refresh this data that's in memory and keep processing going. So we have to do that in a transactional fashion so you don't suddenly have an empty cache. So you effectively have a working copy in memory, and then you have a copy that's being loaded into memory. And once it's done, then you'll switch to using the new one. And to scale processing, rely very heavily on the stream partitioning, kind of this ability to send your data to a particular node in a consistent fashion based on some partitioning algorithm, some key. And that's really the way that you can scale processing of data across a large number of nodes. And it kind of works a little bit like MapReduce, kind of, because you're mapping out the data to a number of nodes for processing. When you write results, those results are accessible across the cluster. And so that's the way that you can basically scale the results as part of scaling the processing. As I mentioned, the queries that people write and the data flows that they build in our platform, they actually become Java bytecode. And we found that that was a way more efficient way of doing queries and scaling queries than having a general purpose query engine. A general purpose engine or a scripting language or anything else is going to be way less performant than Java bytecode that's generated specifically to actually do that task. And the other type of thing that can live in memory, because this is a streaming platform, you have all these data streams running. Pretty often you want to be able to run queries against a view over the streams, which is called a window. And so that will be asking questions like, what's happening in the last 5 minutes? And so you turn your infinite, unending stream into a kind of bounded set that changes all the time, but it's bounded. So these in-memory windows, they take up memory. So if you're going to scale, then you need to be able to partition. The partitioning is really important then because you're basically scaling the windows across a whole bunch of different nodes. And the result set, as as I said, by default, we're using Elasticsearch. And so a lot of the features of Elasticsearch help us scale the results. It's automatically partitioned, it's replicated, it's all pre-indexed, and so the queries happen really fast against it. But we also had to take into account the fact that we do this sub-clustering. So although you may have a whole cluster, say with 100 machines, you may only choose to write your results out to, say, 4 of them. So we had to handle those situations as well. So let's go on to the next section, which is reliability. On the data ingest side, we use a mechanism for reliability, which is basically checkpointing. And so rather than, there are different approaches to reliability in a kind of cluster distributed in-memory architecture. One way is you basically transfer state. And so every time something changes, you log that changed, and then you transfer those logs to another machine so that you have 2 copies of those logs, so then if something fails, you can restart from the logs. And so you can reload state, you can reload Windows state, you can reload other query state into memory. But we didn't use that approach. The approach that we took was more of a checkpointing approach, which is we keep track of all the events that we've processed and how far they've got down various data pipelines. And so if something fails, we know what the last known good state was. Now, the biggest issue is windows. If you have defined data windows of, say, the last 5 minutes within your application, how do you reload those windows to be in a consistent state when you start up? Because you can't start from an empty window. You can't just say, I'll start from where I left off, because now you have an empty data window. You don't have the last 5 minutes worth of data. Your results are going to be incorrect. So what you need to be able to do is rewind the incoming data to such a position so that it'll fill up all those windows to the right place, and then you start your processing. Now, you can definitely do that on a lot of the data sources that we support, especially if it's a file, right? You can rewind it to a point in a file and start from that point and play on. With change data capture from databases, which is another technology we use, you can rewind in the database logs and replay from a point and then carry on. But for other things, you think about sensors. You have sensors that are sending you data over TCP all the time. You can't go back to all those sensors and say, hey, sensors, send me all your data again for the last 5 minutes. Because 1, you're not going to be able to talk to them in that way. And 2, they probably don't have that data to send to you anyway. So with things like that data is transient, that's where we rely on persistent messaging and a Kafka-based architecture. So as things are being ingested, we immediately store them. And now we checkpoint into the persistent messaging, and we say, we have read from here. So we don't use that everywhere, especially not with the rewindable sources, but with the non-rewindable ones. It's really essential that you can actually persist those things, so if you do need to recover, then you have all that data available. Now with the high-speed messaging, basically if you lose a node, we will repartition if that node goes down. We'll basically say, we used to send the stocks for this company over here. Now that node's gone away, we need to send it over here instead. But we do that in a consistent fashion so that it's always going to be in the same place. With persistent messaging, there's a few tricks that we had to employ in order to kind of get that exactly once type of processing. And the hardest bit for us was knowing whether we'd actually sent something before a node went down and it actually made it into the persistent messaging. So what we did there, we actually have a reader to the same persistent messaging queues or topics that we're writing to. And so as soon as we put something in, we check to see that it's being written and we get it back out again. It only really works with topics, it won't work with queues because they would only have, the thing would disappear. But with a topic, you can basically subscribe to it and you can say, I want to know as soon as this thing that I gave you has been written, now I can checkpoint and say, you safely got it. And if I didn't see it, then you didn't safely get it. And so I need to give it to you again if I fail. That's kind of how the persistent messaging is used for checkpointing to make sure that you only do get this exactly once. The metadata and kind of the whole clustering side of things, that's where we watch for node failure, and also we can detect application failure and failure of certain services. So for example, we have a particular service that's responsible for starting and stopping and deploying applications within our platform, and that's only going to run on one node. If that node goes down, then we'll know about it immediately, and that service will start up somewhere else within the cluster. And these are things that we don't think users should have to worry about. They shouldn't have to manually do any of these things, and they shouldn't have to do complex configuration to get it working. The servers should really try and take care of themselves when it comes to this level of reliability. The in-memory data grid that we use for data, that is inherently replicated. So if you just lose one node, then you'll still have the data, and it will replicate the data out to another node. You can choose a whole bunch of different kind of numbers of replicas from none to the whole cluster. And the key there is that when you do repartition, you repartition alongside repartitioning the high-speed messaging layer as well. So you make sure the two happen at the same time so that you're consistently taking the right events to the right nodes that now have the cache data, whereas they may not have used to have had that particular partition. So you need to take care of all of those things. And I mentioned some of this before. On the processing side, the recovery really has to enable the restore of window content. And that can just be, you're filling this 5-minute window back up, but what if you had some processing that filled a 5-minute window? Based on that, you have some other processing that is looking for trends in that 5 minutes, is writing into another window, and then that window is used somewhere else. You have to go all the way back through this chain of windows in order to actually remember what the state was so you can get it to the right point. Now that's the first half of the equation. The second half is you also have to remember what was the last thing you actually saw go out of the window. Because as you're filling it all back up again, you have to make sure you're not replicating and regenerating all of these events that you saw previously. It's also important you can handle different types of exceptions. You can have things where your system fails. There's some issue and things aren't working, and that could result in a node failure. But then there are other things where it's a data issue, right? So maybe some data is null that you're trying to access, or there's a query that's doing a divide by zero, or some other type of data thing. You need to be able to handle these types of exceptions in a friendly way to users, log them, maybe push them down into a different data stream so that you can process them separately. And then if you do see these things, maybe you want to auto-crash the application so that recovery can kick in, and maybe you fix up your data or fix up your queries and restart from where you left off. And results, a lot of this is handled by Elasticsearch for us, but we do watch what we do right into the results store, and we try and make sure that we do just exactly once results as well. So we watch what we've written into results, and if we are recovering, we check on the storage that we don't store the same thing again. So we use checkpointing for that too. Okay, so on to security. Oops. Now, security covers every aspect of this, every aspect of in-memory computing. On the data ingest side, there's two pieces really. One is if you're defining stuff, if a user's writing some configuration or some code to actually get to some data, maybe that data's in a database or it's on some other system that is secured, make sure that you secure the passwords that people are entering, that they don't enter them in plain text in some script, and that they can be secured in such a way that they're hard to crack. If you saw the news about LinkedIn, please use SALT on any encryption of passwords. It's really important that you can secure anything that users may seem that they don't want anyone else to see, right? And if you have a platform where people can work with different sources, it may be necessary to protect a particular source. If you have a data source that has credit card numbers in it or personally identifiable information, and you're doing some processing on that, and that's going somewhere, it's producing some end result that you want people to see. Maybe there's some wonderful dashboard you've created that's showing all of the financial transactions that are happening in the organization in real time. That's being driven by some raw data. You need to give people access to the end results, but not to the raw data. So you need to be able to secure things differently all along the way and make sure that there's a single consistent security model across everything. As you're moving data, obviously you need to encrypt data on the wire. That's really important that you use modern encryption techniques to ensure that everything that's traveling from one node to another is encrypted. Anything that's going over the network within an organization, it's easily accessible. So make sure it's encrypted. And again, prevent unauthorized access to data streams. And if you're using a third-party messaging layer, so for example, internally we're using Kafka for the persistent messaging, right? You need to secure that because it's easy to connect to a topic if you know what you're doing, right? And there you have access to the full data stream. So encrypt it, and encrypt the data that you put on there, and use a nice salted encryption scheme that isn't easy to crack, even if you have the code. And again, try and prevent unauthorized access to these data streams through a common security model, ideally tied into your enterprise LDAP architecture or whatever your existing user management is. Now, internally within our platform, we utilize the metadata and control data grid to deal with security to a large degree. So it's through this layer that people try and access all the individual components. And so within this layer, we have role-based security with fine-grained access. And so that means you can create a general role that says you can access applications or you can see dashboards. But within that, you can say, yeah, you can access applications, but there's one stream here that has personally identifiable information in it, you can't see that. There's only one guy that can see that. So you need to have a security model that can be broad, so it's easy to work with, but also can be fine-grained so you can protect things as you need to. And then with data processing, there are some things that you should probably care about there, and if you're using Java code, you can secure some of the Java functions that you're doing using a security policy, so people don't use kind of arbitrary Java functions. But the key thing with an in-memory platform is, as much as you possibly can, avoid intermediate data staging, right? So if you're creating a data pipeline, try not to write intermediate files at each stage of the pipeline. Pass things in memory and work with things in memory. It's much safer that way. As soon as things are written to disk, then you can encrypt them, but they're written to disk. So they're much easier to access than something that is transient and in memory and is going to disappear, right? Then overall, I think the major thing with security is try and be consistent, use a single authentication scheme, and think of all of the aspects of in-memory computing that you may be using, all the different components you may be using, and make sure each one is secured. And wherever you're moving data from one place to another, encrypt it. And the final aspect is integration. And for us, integration was essential because it's an in-memory analysis platform, right? It's able to ingest all this data and process it and produce results and visualize it. But without getting to data and without being able to work with what people have already, that isn't much use. So on the data ingestion side, we needed to be able to work with things like message queues. There's lots of different flavors of these. There's MQ series, which goes back about 100 years. And then there's JMS and AMQP and Kafka and Flume and different messaging technologies that an enterprise may have already that you'll have to integrate with, and they all have different APIs and different ways of working with them. Sensors don't really have any standards around them yet, other than they can communicate over lots of different protocols with lots of different data formats, and you may or may not have to do edge processing. So there are some protocols coming up, like MQTT, for example, that is being used in the sensor environment that you may have to integrate with. But then there's all these proprietary gateways and other things that you may have to integrate with. For files, we found with in-memory processing of data in a streaming fashion, working with batches of files after the files have been complete and like doing log shipping isn't the most efficient way of doing it. So we built a way of doing continual reading of files as new data is being written to it. And there's a few tricks there, because depending on how things are being flushed to files, you may have just a partial record. And so you need to make sure that you don't throw it away because it doesn't match your parsing rules, and you wait until it's complete before you actually try and process it. And so it's not as easy as just reading what's at the end of the file. You have to have all this kind of state machine around reading the file to make sure you do get a complete record. And so with our agents and our collection mechanism, you can read files in a parallel fashion, and the data, it'll read at the end of the file as new data is written to it, it'll stream out, and now it's available for processing. Now the final thing with in-memory computing and kind of streaming analytics in general are databases, and databases aren't normally thought of as streaming. They are a record of what has happened rather than what is happening right now. And if you look at most enterprises, most DBAs, they are not going to allow you to run SQL against a production database. They may say, we'll create a read-only replica for you, but you're going to have the same resources as the original database, and it's expensive, and there you can query against that. But what you can do is you can use change data capture. So if you run change data capture against the database, and I'll talk more about this tomorrow. I have a 10-minute lightning round on change data capture tomorrow. If you use change data capture, what you'll see is all of the operations that happen in a database as they occur. And it's a technology that listens to the transaction log of the database. As things happen in the database, they're written to transaction log, change data capture sees it, and now you have real-time events coming out that match what was in the database. So every insert, update, and delete becomes an equivalent event, and it happens with very low latency. So you're now seeing what's happening in a database in real time, and that's a much better match for in-memory computing than running queries against the database anyway. Because one of the issues with running snapshot queries, apart from it being expensive to run against a production database, you can miss things. If someone went in and they changed the value, and then they changed it back again 5 minutes later, and you're running a snapshot every 10 minutes, you're going to miss it. You won't miss it with change data capture. And the key thing really is you want your data collection to move at the speed of the data. The next piece is what kind of processing can you do? There are different kind of categories of things that you'll probably want to do in your in-memory computing platform. One is to filter out unnecessary data and to transform the data into a form that you want. And really this is where kind of the windowing comes in that I mentioned earlier. Be able to aggregate and to remove redundancy or obtain trends over time. If you think about IoT, and if you have like a Nest thermometer and it's sending out a message saying the temperature is 70 degrees, and it's doing that once a second, that means in an hour you've got over 3,500 messages. But if it stayed at 70 degrees that whole time, how much information is that? It's one piece of information. It's been 70 degrees for the last hour. You don't need those 3,500 messages. So if you're thinking about aggregation, aggregation can be used to remove redundancy. It can also be used to look for trends over time. And an important thing with integration is being able to integrate with existing functionality. If you have Java code that's been written already, or you have models that you've built in R or SAS, and you want to use those models in memory, you need to be able to integrate with those. So you need to be able to think out, how do I integrate these existing models and this existing processing into my in-memory computing platform? And then the final piece is really on the delivery side. Again, like the sources, you need to think about all the different types of things you may want to deliver to, and they all have different characteristics and different ways you have to work with them. Some of them are transactional, like databases. Some of them are on-premise. Some of them are out in the cloud. Some of them you have to think about data partitioning, like if you're delivering into Hadoop. So there's different technologies and different approaches that you can take for each one of these things, but they all have to work well with the security and with the reliability and with the scalability that has been defined before. So there are different tricks that are needed for each one of these different technologies. And then the other part for integration is being able to load large amounts of data into memory, and to do that for the purpose of processing. So what we've seen is a lot of raw streaming data that people get doesn't have sufficient context for you to actually run queries or analysis against it. And I'll give you an example. In the telco space, they have these call detail records. Call detail records are basically a record of every call that happened and what the signal strength was, whether the call was successful or not, where it was, etc. And within that record, there's a whole bunch of hex codes that represent different things. And one of those hex codes might be the serial number of the phone. Another one might be your subscriber identifier. Now, you try running analytics over that. You're not going to get a lot of information out of it because you have a whole bunch of hex codes. So that's where one of our customers loaded, I think it was 40 million of their customer records into memory. And so as the data's flowing through, they're joining that high-speed streaming data with the subscriber identifier in it with their customer records. So now they have all this information about the customer as context for their processing. And the other point, if you're not building a platform that you want people to kind of use easily, you don't have to pay attention to this. But if you are building something that you want people to work with, then user experience is really important. And if you have all this capability and ability to define data flows and analysis and visualize results in dashboards, you need to have a common user experience that hides the complexity of the in-memory computing platform from the people. And this kind of technology can be applied to a whole bunch of different use cases. It can be as simple as I want to collect database change and move it into Hadoop or push it into Kafka and do that in real time. But it can also be incredibly complex, of preventing fraud or unusual activity or enhancing customer experience. And as soon as you start to move into the mission critical side of things, that's when all of the enterprise grade characteristics really come in. Because if you're running fraud analytics, you want to make sure that that's working and that it's scalable and it's not going to fail. And just a quick pitch before I end the presentation. Just wanted to tell you guys, I'm very happy that Stream was voted a cool vendor in in-memory computing by Gartner this year. So because we're officially cool, you can actually believe what we're saying about enterprise grade. They did specifically call out that we were enterprise class platform. So a lot of thought has gone into how do you make in-memory computing enterprise grade within our company, and talking with a lot of customers as well. There's two things that you should take away from this. The first is that enterprise grade means that it's scalable, reliable, secure, and integrates well with a lot of other things. And the final one is, if you're not thinking about using streaming technologies to work with in-memory computing, then you're wasting your in-memory computing resources. You need to really be able to get high-speed data as it's happening into in-memory computing, because the two are really matched well. So thank you. And if you want to know more, you can come to our website. You can come over and talk to us. We're just outside. You can email me or tweet to me, whatever you want. Thank you, and I hope you enjoyed the presentation.